The first example we want to talk about is the so-called circle rotation. For any alpha in R, we define the circle rotation by alpha to be the map R sub alpha from T to T, where R sub alpha of T is equal to T plus alpha. And we have to modulo this by 1. This corresponds to a situation where this T plus alpha might be greater or equal to 1. In that case, we want to subtract 1 from here. And here we already identified this topological notion with this interval notion. Then we claim that R sub alpha preserves the Lebesgue measure M sub t on the circle. If you are familiar with measure theory, this should be very obvious to you due to a theorem which states that in order to prove that this map preserves a measure on everything in the sigma algebra, it suffices to show that it preserves a measure for a semi-algebra that generates the sigma algebra. But let me state it carefully over here. First, let's quickly recall a definition from measure theory. A set S, which is a subset of the power set on space X, is called a semi-algebra if it has the following properties. First, the empty set is in here. And second, given two sets in S, its intersection is again in S. And thirdly, if a set is in S, then the complement X minus A is a finite union of pairwise disjoint elements in S. And this is the definition of a semi-algebra. And now the theorem says the following. Let X be X mu and Y be Y mu be two probability spaces, and let S be a semi-algebra which generates the sigma algebra By. Then a measurable map phi from X to Y is measure preserving if and only if it is measure preserving for all sets in this semi-algebra. Namely, if you can verify this measure-preserving property for the semi-algebra that generates the sigma algebra for your target space, then you have the measure-preserving for everything in that sigma algebra. So this type of theorems is very common in measure theory. Oftentimes, in order to verify something for sigma algebra, it suffices to verify it for semi-algebra that generates the sigma algebra. This is very common in measure theory. Another question is, for this specific situation, what is our semi-algebra? The semi-algebra in this situation, remember, we identified this circle with the interval from 0 to 1, and the semi-algebra in this case can be taken as follows. So consider all such intervals a, b, where a is less than or equal to b, and a is greater or equal to 0, and b is less than 1. The reason that I allow a is less than or equal to b, because it is understood that when a is equal to b, that this interval is empty. So this really contains the empty set. And you can see, if there are two intervals here, then their intersection must also be in here. And if you take an interval in here and you take the complement of it in this space, you will get, so if you take 0, 1 minus the interval from a to b, you get the union of the interval from 0 to a and the interval from b to 1, which makes the complement of this to be a finite union of pairwise disjoint elements in S. And now, by using the theorem above and this semi-algebra, we can easily verify that those rotation maps preserves the Lebesgue measures of those intervals. And because this subalgebra generates the Borel sigma algebra on this space, we know by the theorem that R sub alpha preserves the Lebesgue measure of any Borel subset of this. So this example is easy. But now we will talk about a generalization of this. So this will be the generalization of this example to a compact group. Let X be a compact group and let G be an element of X. Then the map T sub G from X to X defined by, so what will be the generalization of this to this situation? This will be T sub G of X equal to G dot X. This map preserves the left hard measure denoted M sub X on X. And here, because X is assumed to be a compact group, we can normalize this higher measure to a probability measure. That is guaranteed by the compactness of the group. And by the left invariance of the higher measure, you can easily see that this map is measure preserving. So those two examples we talked about are really easy examples.